students, I am Ramasubba Reddy. I am your physics faculty. Today we are going to discuss 12th class new chapter, that is atoms. Okay, the neat weightage of this chapter is one question, that is 4 marks will get. These atoms we classified into two modules. Module 1 will discuss the concepts. Module 2 will discuss the problems which is related to Module 1. So in Module 1, again the concepts we broadly classified into three. First one, what is J.J. Thomson model? Means what is the J.J. Thomson structure of atom? What is the limitations? And what is the experimental set to find specific charge of electron? That is the charge of electron by mass of electron. And next, Millikan oil drop experiment. By using the Millikan oil drop experiment, we'll find the charge of electron, that is 1.6 into 10 to the power of minus 19 coulomb. Next, Rutherford scattering experiment. When gold foil is incident, means when alpha particle is passing through incident and a gold foil, what are the scattering angle, what are the observations, what are the conclusions we'll discuss. Okay, then next, Rutherford nuclear model of atom. What are the postulates, what is the limitations, we'll discuss. Then next we'll discuss Bohr theory of atom. Okay, I will share the screen. Bohr's theory of atom. In Bohr's theory of atom, what is the postulates of Bohr's? What is the Bohr's hydrogen model? What is the hydrogen energy? Okay, what is the hydrogen radius? What is the hydrogen velocity and frequency time period? That all will discuss. Okay, so the neat weightage of our chapter, 1 minute. Yes, neat and JE weightage is one question we'll get here, that is 4 marks. Okay, then what is the atom? First of all, atom is a basic building block of matter. If any matter, definitely atom will be there. That is the basic building of matter. We know the atom consists of three basic particles: electron, proton and neutron. Then we already discussed the outline, the brief outline of the chapter. What is J.J. Thomson model of atom, and what is the experimental determination of specific charge of electron, that is the ratio of charge of electron by mass of electron. What is the Millikan oil drop experiment and how to find the charge of electron. Then second one, Rutherford scattering experiment. When alpha particles are going to incident on gold foil, what are the scattering angles will vary. Okay, we'll get some conclusions. That conclusions are very important. And later Rutherford gave one model, that is a nuclear model, which is related to these observations of Rutherford scattering. Next, Bohr's atom model, and in that we'll discuss the hydrogen and what is the hydrogen radius, time, velocity, frequency and energy. And hydrogen spectra we discuss. In hydrogen spectra we have Lyman, Passion, Bracket, Fund series, different series. What is the initial value and final value, and one is what and two is what, and what is the maximum wavelength, what is the minimum wavelength, we'll find. Then the limitations in sports model also we have some limitations we'll discuss. So this is the broad outline of our atom chapter. Now first one we'll see J.J. Thomson model of atom. So this is the first model of atom which explain the structure of atom, how they arrange the electron, proton, neutrons internally. Okay, he proposed that each atom consists of negatively charged particles called electron. Each atom is consist of negative charge particles. That negative charge particles he called electrons. Then second postulates, second point, since atom is whole is neutral, atom whole is neutral. In this atom center we get the nucleus and the electron is revolving and plus and minus. So the atom pole is neutral, so there must be positive charged particle in the atom such that the net charge on the atom is 0. Now we know at central is nucleus, that is positive charge. When J.J. Thomson found these assumptions, he didn't know the value. That's why he assumed that and there must be a positive charge of the particle in the atom in order to make neutral. Next, third postulate. An atom is a sphere of positive charges of uniform density of about 10 to the power of minus 10 meter diameter. So, in which negative charges are embedded like plums in the pudding. So, what is the meaning of that third postulate? An atom is a sphere of uniform density. Okay, this sphere has the uniform density. Uniform density of about, they gave the size 10 to the power of minus 10 meter diameter, in which negative charges are embedded like plums in the pudding. So here negative charges are embedded like this, plums in the pudding. And Thomson model of atom is therefore also we called plum pudding model. This model we also call plum pudding model, and we also called watermelon model. Watermelon model. What is watermelon model? If you observe the watermelon, inside will get red. That red is uniformly density of positive charges. These all are uniform density of positive charges. And here if we observe, we have the black seeds. That seeds are embedded like electrons. So this J.J. Thomson model also we call watermelon model. Next, fourth one, Thomson predicted if a beam of alpha particles passed through an atom, it suffered only a small deflections due to weak electric forces exerted on it by positive charges. So what he predicted, if you take the beam of alpha particles, this beam of alpha particles are passing through an atom, it suffered or it experiences small deflections, very small deflections. Here also small deflections due to alpha particles also have positive charge, and according to J.J. Thomson, positive charge is distributed the entire sphere, so repulsion force will be there. So you get small deflections are weak electric forces exerted on it by positive charges. Okay, so that is the four assumptions or four postulates of our J.J. Thomson model. And then what are the limitations? He is not able to explain some phenomenon. That is first one, he didn't explain how the positive charges were uniformly distributed the entire sphere. That is one drawback. Later, Rutherford, he is the student of J.J. Thomson. He proved that the positive charges were not uniformly distributed in a sphere. Okay, J.J. Thomson mentioned positive charges are uniformly distributed in a sphere. Later, student Rutherford proved that no, it is wrong. Then that is first limitation. Second one, Thomson model could not explain. Thomson model could not explain the large angle scattering of alpha particles when incident on thin metallic foil, say gold foil. So Thomson model is not able to explain the large deflections. We discuss if beam of alpha particles are passes through incident an atom, let us say it is a gold foil, there will be a small deflections and large deflections, but he is not able to explain the large angle scattering. That is the limitations of J.J. Thomson. Okay, but J.J. Thomson, he find the specific charge of electron, specific charge that we'll discuss. Specific charge. For that, we'll get experimental setup, experimental determination of specific charge of an electron, that is E by M. Okay, experimental determination of specific charge of an electron. So here we will see the cathode. C is the cathode. Here cathode, the rays coming out from cathode we called cathode rays. Cathode rays. When these cathode rays are passes through electric and this is magnetic field perpendicular, it is undeflected and moves straight at the point S. So at the cases, what is the velocity? So that is our main task to find. Okay, now we will see the construction of our experimental setup. Here this is E1 and E2. We have the two plates. In this case, E1 is connected to positive terminal, E2 is connected to the negative terminal of the battery. Then this is our electric field direction from E1 to E2. And this is a magnetic field. We make one circular coil in clockwise direction. The magnetic field is in. So two electric and magnetic field is there. Now first we will see when electric field is present, what will happen. When electric field is present, when electric field is present, the electron is moving along this electric field. Of when it is moving the electric field electron, it is going to deflect S1. Okay, then what is the force when electric field is present? When electric field is present, we have the force, that is Fe is equal to E into E, and where it is deflected to the point S1. Next, if magnetic field is present, means only magnetic field, here only electric field, here first case only electric field, second case is only magnetic field. So if this magnetic field is applied by using clockwise current, circular coil, the direction of magnetic field is directed into the plane of the paper. Then Fleming left hand rule, we can find where the motion of electron will move. So by Fleming left hand rule, we'll find the direction of electron is going to incident on S2. In this case, we have the magnetic force, that is, what is magnetic force? DeV. That is, only electric and magnetic field are applied. Now if we apply simultaneously both simultaneously both electric and magnetic field. What will happen if we apply both simultaneously electric and magnetic field? The electron moving perpendicular to the direction of electric and magnetic field, it is undeflected and strikes the point S. In this particular case, our magnetic force is equal to electric force. Okay, magnetic force we know BeV, and electric force we know E into E. E get cancelled. Then electric, or we need to find velocity. Velocity V is equal to E by B. Okay, that is our formula, important formula. They will ask in problems when the charge of an electron is moving perpendicular to the direction of electromagnetic field. What is velocity? V is equal to E by V. And then our aim is to find specific charge, that is E by M. How to find? In order to get E by M, this electron is accelerated. This electron is accelerated from cathode to anode. Cathode to anode. Then definitely there will be some work is done on electron by the accelerating voltage is equal to increase in kinetic energy. That we know. Then that kinetic energy of electron at anode is equal to work done on the electron. Then kinetic energy of mv square. If it is a potential, we have the relation E into V naught. Then if you see here, this one, E by M is equal to V square by 2 V naught. Now, we have E by M is equal to V square by 2 V naught. So where V naught is the potential difference between cathode and anode. Cathode and anode. And M is mass of electron. Mass of electron. E is charge of electron. And V is the velocity of electron. And just now we find what is the velocity of electron is E by B. This will substitute here. Then our E by M is equal to E, in the place of E it is E by B whole square and 2 V naught. It is 1 by. Then E by M is equal to E square by B square 2 V naught. So this is our specific charge of an electron, or E by M ratio. So we can find E by M easily. How? We know the electric field, how much we applied, and we know the magnetic field, and we know the potential. So definitely we can find. So that E by M for electron is 1.7588 into 10 to the power of 11 coulomb per kg. Okay, very important this value. That is our specific charge of electron, a ratio of charge of electron by mass of electron. Next we will discuss the Millikan oil draft experiment. This experiment is used to find the charge of electron. That is 1.6 into 10 to the power of minus 19 coulomb. Now we know the charge of electron, we can say easily. Before he done an experimental setup like this, and he found. Now we'll see the experimental setup. What is the experimental setup, and what is the phenomenon he used in order to find the charge of electron? Here, in order to find the charge of electron, Millicon, he used the terminal velocity. He measured the terminal velocity. Terminal velocity of charged oil drop. Charged oil drop under action of gravity and electric field. Okay, so that is the main concepts to find the charge of electron. We know what is the terminal velocity, at which the velocity at which it is moving with constant, that is one. Another one, where the net force is equal to 0, from that point onwards the velocity moving constantly. Okay, now what is the working of our Millikan oil drop experiment? So a electric field is applied between the plates. Here this is the one plate A and this is another plate B. Then electric field is produced between the plates A and B. Okay, here small droplets of non-volatile. Here we are taking non-volatile oil. Non-volatile oil. That non-volatile oil are clock oil or Epigean oil. That small droplets are coming out from this atomizer and they are sprayed. This non-volatile or clock oil or Epigean oil will be there in atomizer. So this will be sprayed. So this will coming and spray using atomizer above the hole of the plates. Here in this hole of the plates. So when these oil drops are coming, what will happen? Some of the droplets acquire charge. Some of the droplets are acquire charges due to friction. Some of the charges acquire the charge due to friction. That charge we need to find. How to find? For that we are sending a light. We are illuminating the light to that charged particle and we can view by using the telescope. Now the drops can be seen by using a telescope which is placed perpendicular to the light beam. If a drop looks like bright star, then a drop looks like bright star. Either it is moving upward or downward, depending on the conditions. Okay, now we'll see an electric field is produced between the plates A and B. Now we are producing the electric field between A and B. Upper plate is connected to the positive terminal of the battery and lower plate is connected to the negative terminal of the battery. Okay, this is our direction of the battery. Then what will happen? The field is adjusted. Now we'll try to adjust the field. The field is adjusted so that oil drops slowly moves upward. Slowly move upwards, and these drop experiences electric forces and buoyancy in the upward direction, whereas weight and viscous force in the downward direction. Okay, now we'll see the concepts. First one, case one. We will see without electric field. Case one is without electric field or in the absence of electric field. Okay, in the absence of electric field, what will happen? The charge of drop is experiences buoyancy force, upward, and viscous force and weight. that is mg, which force gravitational force. This is the conditions when we consider the oil drop is without electric field, and this oil drops falls downward with some velocity v1. Now when we'll get net force is equal to 0 at the time the drop is moving constant velocity, that is terminal velocity. This net force is equal to 0 means what does it mean? Buoyancy force plus viscous force minus Fg is equal to 0. Then Fg is equal to buoyancy force plus viscous force. Buoyancy force is what? Buoyancy force, if you place any object or immersed in water, there will be some upthrust or upward force. That upward force is buoyancy force. And viscous force is the force which is opposed the motion of the fluid. Then Fg is equal to m into g, that is mass of oil into g, that we can written as g. And buoyancy force, this is air into g, and viscous force 6 pi neta rv, but here it is v1. This also we can written as density into volume, that is mass 4 by 3 pi r cube density of oil into g, which is equal to here 4 by 3 pi r cube, this is density of air, into g, plus 6 pi neta rv1. Now if you rearrange this equation, 4 by 3 pi r cube into g, density of oil minus density of air, which is equal to 6 pi neta rv1. Okay, now 2 2 2 3 3 3 9. So 1 pi get cancelled, 1 r get cancelled. What will get? 2 r square g density of oil minus density of air is equal to 9 neta v1. So from this we will find 9 neta v1. From this we can find the radius of the oil drop. That radius of oil drop r is equal to, this all will come to denominator, 9 neta v1 by 2g density of oil minus density of air all to the power of 1 by 2. Okay, this is important. That is our radius of oil drop. Now we will find in the presence of electric field, case 2, that is with electric field. So with electric field condition we will find the charge of electron. So that is our main aim. So in this case, this is our oil drop is moving velocity v2 with upward. This experiences electric force upward and buoyancy force upward and gravitational force downward and viscous force is downward. Now the total force is 0, net force. In this case, what upward force is equal to downward force. Then buoyancy force, F buoyancy force plus F electric force is equal to F gravitational force plus F viscous force. Okay, F buoyancy force is 4 by 3 pi r cube density of air plus electric force Q into E, gravitational force m into g, that again we can written as 4 by 3 pi r cube density of oil to g, and viscous force 6 pi neta rv2. Here I wrote directly because same only we wrote in first term. Okay, buoyancy force m into g, here g will get. m into g. M is 4 by 3 pi r cube, that is density into volume. So this is volume and density is sigma L. Here same mg density into volume. Volume is 4 by 3 pi r cube, density is rho of I. Now from this what we'll get, 4 by 3 pi r cube into g density of oil minus sigma of air, which is equal to this QE come to this side, or this 6 pi neta R1 will come to this side, QE minus 6 pi neta RV2. If you observe this equation, which is equal to this value only now, this value 4 by 3 pi r cube g density of oil minus density of air is equal to 6 pi neta RV1. Let us take equation 1. So here we'll substitute that value, which is equal to 6 pi neta RV1 is equal to QE minus 6 pi neta RV2. Then charge of oil drop Q is equal to 6 pi neta R. This will come to this side now, that is V1 plus V2. Here E will be there, that will write downside. Okay, that is our charge of oil drop. Now if we want to substitute radius, where neta is what? Coefficient of viscosity. Radius we find, we will substitute here, we will get our charge Q is equal to 6 pi neta, radius is 9 neta V1 by 2g density of oil minus sigma of air all to the power of 1 by 2 V1 plus V2 by E. This is our charge of oil drop. Okay. Charge of oil drop. So after substituting all constant values, we'll get 1.6 into 10 to the power of minus 19 coulomb. This is our charge of electron. Clear? So very important. From this model also we'll get in exam. Next one, we'll see Rutherford. Rutherford Geiger Marsden experiment. So Rutherford done some experiment with his colleagues Geiger and Marsden. So what is the experiment? Why he done this experiment? We'll discuss in detail. So here we have, this is alpha particles, source of alpha particles. So what is alpha particles? This also we called alpha particle scattering by thin gold foil. This also we called alpha particle scattering by thin gold foil. Okay, alpha particle scattering by thin gold foil. So here we have to know source of alpha particle. Our alpha particle's charge is plus 2e and mass of alpha particle is equal to 4 times of mass of proton, and alpha particle is generally denoted by He2 plus. Okay, and where we'll get alpha particles, we'll get bismuth 83214. From this element we'll get alpha particles. This we kept in a lead cavity, this element. Okay, now here we have, this is from this bismuth we'll get the beam of alpha particles. That beam of alpha particle is going to strike the thin gold foil of thickness 10 to the power of minus 8 meter, very less thickness. Okay, now we will see the working. So when a beam of alpha particles passing through incident on a gold file are scattered by the gold file, the scattered alpha particles fall on the fluorescent screen. This is our fluorescent screen. This is a mobile detector. We will find how much the alpha particle is deflected and how it is changing with angle. Okay. When a beam of alpha particles are scattered by thin gold file, these scattered alpha particles fall on a fluorescent screen and scintillations will occur. Scintillations will occur. What is scintillation? Like flash. These scintillations are observed to this movable detector. Means when this beam of alpha particles are scattered, when this is incident on here, like this, scintillations will occur like this, like one flash. That flash will observe by movable detector. That is the working of Rutherford Geiger-Marsden experiment. Then what he observed from that, he observed most of alpha particles are passed through the gold file are undeflected. You see, this is our stream of alpha particles. These stream of alpha particles are going to thin gold file. Most are undeflected. They are moving in straight. Some only deflected. Okay, passed through the gold file are undeflected. That he observed. Second one, some of alpha particles are about 0.14% of the instant alpha particles were deflected through small angle. Okay, some of the alpha particles are deflected through small angle when like this. Alpha particle going through the gold file, now this is gold file. They will some only out of 100 will get only 4 to 5. That deflected with a small angle that is less than 1 degree. Third point, few of alpha particles that is 1 in 8,000 were deflected through large angle, maybe greater than 90 degree. Some of them even retraces their path, that is the angle of deflection was 180 degree. Okay, some of them as retracing their path. This is stream of alpha particles. This is the gold file after incident. It is retracing the path that he observed, and very few particles will scattered with large angle. Next, fourth one, the number of alpha particles per unit area, that is n of theta, that reaches the screen at scattering angle theta were found is n of theta is inversely proportional to 1 by sine to the power of 4 theta by 2. That is important condition. And this is our graph. Then conclusions. These conclusions are very important. What he get the conclusions based on his observations. So most of the alpha particle passes through the gold file undeflected. That we observe in observations. What does it mean? Means, so it indicates that most of the space in the atom is empty. If you take this is the atom, most of the space in the atom is empty. This most of the space is empty. That here get the conclusion. Second one, alpha particle is positive charge and having the large mass as compared to the electron that we already discussed, could only be deflected backwards due to the repulsive force, or repulsive force due to heavy and positive charged region. So Rutherford concluded that positive charges in an atom are concentrated in a very small region at the center of the atom. So if we consider this is our atom, only at center it is located, that he found the conclusion. But actually in J.J. Thomson, what he mentioned, the positive charges are uniformly distributed. That he proved wrong because of this experimental setup. Then he found at center only we have heavily positive charge. That's why repulsion force will taking place. Okay, then he called that heavy and positive charge region as nucleus. He called that as nucleus. Okay, that is the conclusions. Very important one, these conclusions. Next, we have some definitions related to this experiment. Alpha particle trajectory and impact parameter means how the alpha particles get the trajectory and what is the impact parameter. Okay, now this is our beam of alpha particles passing through the nucleus. Okay, this is a trajectory. Some of them will deflect like this, some of will move this like straight, and some of the deviated, some of them retraces the path. That is the trajectory. Now we'll see the impact parameter. What is the definition of impact parameter? So generally impact parameter is denoted by B. The perpendicular distance of the velocity vector u bar. So this is our perpendicular distance of velocity vector, means this velocity vector is u bar of incident alpha particle. This is our incident alpha particle from the center of the nucleus. So incident of alpha particle is at center, and this is velocity vector u bar. Okay, then this perpendicular distance is called impact parameter. Clear? Impact parameter is what? So this is the perpendicular distance. Actually this is the perpendicular distance of velocity vector u bar and direction of incident alpha particle from the center. This is the center, and this velocity vector u bar. That perpendicular distance we called impact parameter B. Okay, that is the definition. Next, scattering angle. What is the scattering angle? The angle between the direction of approach of alpha particle and the direction of scattered alpha particle is called scattering angle theta. This is direction of approach of the alpha particle and the direction of scattered, that we called scattering angle theta. Okay, and here we have the relation for impact parameter. B is equal to ZE square cot theta by 2 by 4 pi epsilon naught E, or this also will write ZE square cot theta by 2 4 pi epsilon naught E of mu square. This is important relation. Okay, impact parameter. Next, we have another definition, that is distance of closest approach. What is the distance of closest approach? First, this is denoted by R naught. So that is the minimum distance up to which an energetic alpha particle traveling directly towards a nucleus can move before coming to rest and retracing its path is known as distance of closest approach. Means this is our energetic alpha particle is moving towards the nucleus. This is move, and before coming to rest, if it is moving here, it will be rest. It is before coming to rest, again it is retracing the path. So that minimum distance from the center of the nucleus to here, that is R naught, that is distance of closest approach. Okay, so the distance of closest approach generally denoted by R naught. That directly we'll see the relation for distance of closest approach. Expression is the R naught is equal to 1 by 4 pi epsilon naught 2 ZE square by of mu square, or kinetic energy, or R naught is equal to K 2 ZE square by kinetic energy, where K is 1 by 4 pi epsilon naught. This is our distance of closest approach. Okay, remember this relation, important relation, distance of closest approach. Naught is equal to K 2 ZE square by kinetic energy. Now we'll see the Rutherford nuclear model of atom. For this, derivation is there. The derivation is known. You have to remember this formula for solving the problems. Okay, The next, Rutherford's nuclear model of atom. What is the Rutherford nuclear model of atom? Rutherford's nuclear model of atom. He proposed this model on the basis of results alpha scattering experiment. Just now we discussed the alpha scattering experiment. Based on the conclusions and observations of alpha scattering experiment, he gave one model, that is a nuclear model of atom. According to Rutherford's nuclear model of atom, first postulate, almost all of mass of the atom and all the positive charges of an atom are concentrated in a very small region named as nucleus. That's we all discussed. Almost all of mass of this complete atom is concentrated at center, that is positive charge, that he called nucleus of atom. That is first one. Second, the size of nucleus is extremely small. This is extremely small, that is nearly 10 to the power of minus 14 to 10 to the power of minus 15 meter as compared to the size of atom. Okay, this is a whole atom, this is a nucleus. This nucleus is very small compared to the atom. They gave the diameter 10 to the power of minus 10 meter. That is second postulate. Third postulate. The negatively charged particles known as electrons revolve around the nucleus, so most of the space in atom is empty. So this is our atom here, this is our nucleus, and the electrons are revolving around the nucleus. That's why he mentioned, so most of the space in atom is empty. Next, fourth one, the number of revolving electrons is equal to number of positive charges. So how many electrons are revolving is equal to number of positive charges. Then it becomes electrically neutral. That is the postulate of Rutherford. Then we have some failure of this model. He is not able to explain the stability of atom. Simply he is mentioned number of electrons is equal to number of protons, or positive charges is equal to the negative charge, then it will be hence equal like that. So it is not like this. That is the one drawback. Another one is he failed to explain the spectrum emitted by the atom. So he is not able to explain the spectrum emitted by the atom. So that is another drawback. Next, we have Bohr's model of hydrogen like atom. So why we will get the Bohr's model of hydrogen atom? Because in order to explain the concept of stability and spectrum of atom, Bohr used Planck's quantum theory of radiation. So there in Rutherford nuclear model, we have the two limitations or drawbacks, that is stability of atom is not able to explain, and another one is spectrum of atom. So that too can be explains Bohr's model of hydrogen like atom. Here they took the Planck's quantum theory of radiation. Okay, Planck's quantum theory of radiation. This is the quantum mechanics classic approach. So according to Bohr's, he gave the postulates. These postulates are very important. An atom has a small positive charged core called nucleus, where whole mass and positive charge of atom are supposed to be concentrated. So he is validated the point of Rutherford. So same, we already discussed in Rutherford. Next, an electron revolve around the nucleus with definite fixed energy in a circular path. Here is mentioned the electron revolving around the nucleus. Okay, this is the nucleus. This is electron revolving around the nucleus in a circular path of fixed radius. Radius is fixed, is known as stationary state. That state he called stationary state. So the stationary state means what? Without gaining or losing the energy. They didn't gain or lost energy. Then the stationary state also known as energy level, that he is mentioned. Okay, then third postulate, Bohr quantization condition for angular momentum. He states that electron revolving only in certain energy levels in which angular momentum is equal to integral multiple of h by 2 pi. Means L is equal to mvr, which is equal to nh by 2 pi. So in that particular cases only we'll get quantization condition. That is the third one. Next, fourth postulate. An electron emits energy in the form of photon, radiation, or when it jumps from higher energy level to lower energy level. So let us take this is n is equal to 1, n is equal to 2, n is equal to 3. So electron emits the radiation or photon when it is jumps from higher energy to lower energy. Okay, that the energy is h nu, which is equal to delta E, or E initial minus E final is equal to h nu. This is called Bohr's frequency condition. Bohr's frequency condition. Important to this postulates. Okay. Then next. In Bohr's model, we have the radius. What is the radius? We need to find first. In Bohr's, he gave the formula for radius of electron. So we know the electron is revolving in a circular path. Electron, this is a nucleus Ze, and when it is revolving in a circular path, the centrifugal force is balanced by Coulomb's inverse square law. Why? Here we have two charges. What is the Coulomb's inverse square law? That is 1 by 4 pi epsilon naught q1 q2 by r square, which is equal to, this is Coulomb's inverse square law, which is mv square by r, that is centrifugal force. Here 1 by 4 pi epsilon naught, q1 is E, q2 is Ze by r square, that is radius, and mv square by r. So from that mv square is equal to, from here 1r get cancelled. What will write? Ze square by 4 pi epsilon naught r. That we have to remember. mv square is equal to Ze square by 4 pi epsilon naught r. But actually we need to find the radius. Then from quantization of angular momentum, mvr is equal to nh by 2 pi, which is equal to angular momentum L. Okay, then let us take this is equation 2. Now we will see, we'll do 2 square divided by 1. So 2 square means what will get here? M square v square this side by m v square. So m square v square r square by m v square. This is the 2 square of LHS. Now RHS side. 2 square is n square h square by 4 pi square, this value. This one numerator will go and denominator will shift it. Now this can be written as this divided by this value. Here I wrote it directly. This will written as 4 pi epsilon naught r Ze square. Okay. Now m 1m it will be cancelled. 1m. Here it is m r square v square. V square get cancelled. 1 pi get cancelled. 1r get cancelled. Okay, then finally we'll get m r is equal to n square h square epsilon naught. This is m r square, n square h square epsilon naught r. If you take this r as it is, by Ze square pi. So again we cancel this one. Then finally our r is equal to n square h square epsilon naught, n square epsilon naught by m pi z e square. So this is our radius of electron in Bohr hydrogen model. Very, very important. If it is nth orbit, how to get for nth orbit? If it is nth orbit, radius Rn is equal to n square h square epsilon naught by m pi z e square. Then radius Rn is directly proportional to n square by z. Okay, for first orbit, n is equal to 1, then our R1 is equal to 0.53 angstrom. That we have to remember. While solving the numericals, we'll use these values. For first orbit, 0.53 angstroms. Okay, now we'll find the velocity of electron. Velocity of electron in Bohr hydrogen atom. We know from quantization of angular momentum, that is mvr is equal to nh by 2 pi. From this we'll get one velocity, v is equal to nh by 2 pi mr. If it is nth orbit, vn is equal to nh by 2 pi m rn. Just now only we find rn, that is equal to n square h square epsilon naught by m pi z e square. Now we'll substitute here. Then our vn is equal to nh by 2 pi m. Rn is n square h square epsilon naught, this one, m pi z e square, m pi 1n h, then vn is equal to z e square by 2nh epsilon naught. This is for our velocity for nth orbit. Very, very important relation. Means our velocity for nth orbit depends on z and n. If it is for first orbit, n is equal to 1. If n is equal to 1, our v1 is equal to, z is also 1, e is charge, we will get v1 is 2.2 into 10 to the power of 6 meter per second. This also you have to remember for first orbit. And generally, more generalized, we can use velocity v is equal to c by 137. Okay, this is also velocity, very, very important. After substituting the all constant values, we'll get v is equal to c by 137. Next one, time period. What is the time period? We know when electron is revolving in a circular path, time period t is equal to distance by velocity, that is circumference, distance 2 pi rn by velocity v, that is vn. If it is nth orbit, we'll discuss. We know rn value and we know vn value. Just simply we'll substitute, we'll get our time period. Then t is equal to 2 pi, rn value is n square h square epsilon naught by m pi z e square whole divided by vn value, z e square by 2nh epsilon naught. Okay. Now if you simplify that one, this will get 2 pi n square h square epsilon naught by m pi z e square, here also z e square, this will go upside, 2nh epsilon naught. nh. So what are the cancellation? Is there any cancellation terms? Okay. pi will cancel. Then remaining will be there as it is. So this will be written as T is equal to 2 into 2, 4 n square n cube h square h cube epsilon naught square by here m z square. So z square e to the power of 4. That is our time period. Very important, this relation also. Okay, then frequency, it is just reciprocal of that. Frequency is equal to mz square e to the power of 4 by 4n cube h cube epsilon naught square. That is our frequency. Okay, most important these relations. Next we'll find the energy. What are the energies of this Bohr hydrogen? This is also important. So here this energy, kinetic energy, we know kinetic energy. First we'll find kinetic energy is of mv square. First we discussed it. Mv square, what will get? Ze square by 4 by epsilon naught r. We know this value, where first we discussed this value. Okay, that we will substitute here. Then our kinetic energy is equal to of Ze square by 4 by epsilon naught r. Then kinetic energy is equal to Ze square by 8 by epsilon naught r. That is our kinetic energy of electron in Bohr hydrogen model. Then potential energy. This is also nothing but electric potential energy. This is electric potential energy is equal to, what is formula? We have 1 by 4 pi epsilon naught q1 q2 by d, electric potential energy, which is nothing but 1 by 4 pi epsilon naught Ze and minus E by R. Then the potential energy is equal to minus Ze square by 4 pi epsilon naught R. That is our potential energy. Now total energy. Total energy. Total energy is what? The sum of kinetic energy plus potential energy. Then total energy is equal to, that is Ze square by 8 pi epsilon naught r kinetic energy minus Ze square by 4 pi epsilon naught r. Then finally we'll get our total energy is minus Ze square by 8 pi epsilon naught r. That is for energy of Bohr hydrogen model atom. Now if it is for nth orbiter. If it is for nth orbiter, how to find? This one we'll find if it is nth orbiter. For nth orbiter, our total kinetic energy is equal to minus Ze square by 8 pi epsilon naught, that is Rn. Then total energy is equal to minus Ze square by 8 pi epsilon naught. Rn value we know, n square h square epsilon naught by m by Ze square. Then total energy is equal to, finally after calculation, minus Z square e to the power of 4 m by 8 n square h square epsilon naught square. This is our total energy. Z is constant, E is constant, M is constant. So all are the constant. After substituting the constants, we will get minus 13.6 Z square by N square. This is our more generalized energy for hydrogen atom. Okay, if N is equal to 1, that is ground state. If N is equal to greater than 1, we will get excited states. Excited state. Then we have the relation of kinetic energy, potential energy and total energy. So kinetic energy is 1 is to Potential energy minus 2 is to total energy minus 1. This we have to remember. Ratio. Sometimes they may ask the ratios. Okay. So this is all about hydrogen model of Bohr. Next, we'll see the hydrogen spectra. Hydrogen spectra. When we get the hydrogen spectra means when electron jumps. When electron is jumps from higher energy level N2 to lower energy level N1 in stationary atom, the differences in energy is there. That is E2 minus E1 is equal to h nu. That energy is emitted some spectrum. Okay, E2 minus E1 is equal to h nu. Then h nu is equal to E1 is, we know, generally E is equal to minus 13.6 z square by n square in electron volt. So E2 will write 13.6 z square. Can you write this one? 1 by n1 square minus 1 by n2 square. Okay. In terms of joules or in terms of electron volts. In terms of joules, this multiply with 1.6 into 10 to the power of minus 19. That energy is equal to what? H nu, that is Hc by lambda is equal to 13.6 into z square into, I will multiply with 1.6 into 10 to the power of minus 19 converted into joules, and 1 by n1 square minus 1 by n2 square. Then after Hc value also will come this side. Then only 1 by lambda is equal to, we'll get, this is R infinity value into z square 1 by n1 square minus 1 by n2 square. This is meter inverse. This is our more generalized form to find the wavelength of hydrogen spectra. Okay, this is equal to mu bar, that is wave number, where R infinity is the Rydberg constant. What is the value? 1.097 into 10 to the power of 7 meter inverse, and Z is equal to 1 for hydrogen. Okay, so 1 by lambda is equal to R infinity Z square 1 by n1 square minus 1 by n2 square. Very important. In order to find the spectra of hydrogen of different series, we'll use this relation. Now we'll see how to find the and what are the series. What are the series? We'll see here. We have Lyman. We take the spectrum now. Spectra. In this spectra we have like this. This collection of series we called spectra. So Lyman series, Balmer, Paschen, Brackett, and Fund. Lyman series final position is n1 and the initial position is n2, and the series limit for minimum is lambda is equal to 911 angstroms, for maximum 4 by 3r. And in which region they located? UV region. Next, Balmer, n1 is equal to 2, n2 is equal to 3, 4, 5 lambda values and region. Similarly, Paschen, Brackett, and Fund. Now, we see how to find the maxima and minima value. We'll take one series and we'll find Lyman series. In order to get lambda maximum, our n1 is 1, our n2 is 2. Then lambda max we need to find. What is the formula? 1 by lambda is equal to R Z square 1 by n1 square minus 1 by n2 square. N1, n2 we know, 1 by lambda R. Z is 1 for hydrogen, It is 1 by 1 square minus 1 by 2 square. That is 1 by lambda is equal to r. LCM if you take, what will get? 4 minus 1, 3. 3 by 4. We need to find lambda maximum. Lambda max, that is equal to 4 by 3r, and we know r value 1.09 into 10 to the power of 7. If we substitute that r value here, we'll get our lambda max. Lambda max is equal to, what we get here in table, we wrote that value, lambda max for maximum 4 by 3r, that one. Okay. If we want to get the number now, we have to use this r value. That is the procedure to find maximum value. Then similarly, how to find minimum value for Lyman? In order to find minimum value, definitely this electron is jumps from infinity to first orbit. Then 1 by lambda is equal to r. Our n1 is first orbit, n2 is infinity square, which is 1 by lambda is equal to r. Then lambda minimum is equal to 1 by r. R value we know, we will substitute, we'll get the minimum. Similarly we can find Balmer, Paschen, bracket and fund. Okay, they will ask in exam how to find the maximum and minimum wavelength for different spectral series. Clear? Now we'll discuss the Bohr hydrogen model. All concepts we discuss. Now we'll discuss the limitations. What are the limitations of this Bohr model? There will be some points. It could not successfully explained or successfully applied only for a single electron atom. Means it could not able to explain for multi-electron atom. Okay, that is one drawback. It could be successfully applied only for single electron atom. That we have to remember, like He plus lithium 2 plus only is valid. Remaining it is not valid. That is one drawback. And Bohr's model could not explain the binding energy of atoms in the molecules. If you take the molecules, what is the binding energy? That binding energy Bohr's model is not able to explain. That is one drawback. And another is there is no justification was given for principle of quantization of angular momentum. Just is mentioned L is equal to mvr is equal to nh by 2 pi, but there is no proper evidence to get this condition. That is another drawback. Okay. Next one. These three are the major drawbacks. Next, he assumed that Bohr had assumed that the electron in the atom is located at a definite distance from the nucleus. This atom is located at a definite distance from the nucleus and revolving with a definite velocity around it. Have the definite velocity. This is against the Heisenberg uncertainty principle. Why? What is the uncertainty principle? It is impossible to measure accurately and simultaneously both position and momentum. That is delta x and delta p. So how we can say with fixed velocity? Because it is impossible to measure accurately both position and momentum. Position, if we are not able to find position, how will find velocity? Okay, that is the one major drawback. It's not able to explain, and it is violation of the Heisenberg uncertainty principle. These are the limitations. Okay, so what we discussed, what is J.J. Thomson model, and what is J.J. Thomson model? experimental setup, and silicon oil drop experiment we find, and silicon oil drop experiment, charge of electron we discussed, and radius of oil drop we discussed. Okay, next Rutherford scattering experiment we discussed. Rutherford scattering experiment, what is the conclusions, what are the observations. Then hydrogen spectra we discussed. In this hydrogen spectra, what is Lyman, Balmer, Passion, Bracket, Fund, and how to find maxima and minima for different spectral series. Okay, that all we discussed. Okay, this is our module 1. Next, we'll see you in module 2 based on these concepts. Thank you.